Hi guys, it's Mr. Marek. In this video we're discussing electric circuits. You might want to, as you're working through this, pause things and write things down and rewind if you need to hear something again to better your understanding. An electric circuit is something that we can use to create an electric current. An electric current refers to a flow of electric charge. Remember that positive and negative charges push and pull on each other, and we can use the fact that they push and pull on each other to make them move, and when we make them move, we can use them to do work, which is really useful. You may be familiar with water currents, like a flowing river or water flowing through a pipe, and we're going to draw a lot of analogies between the two. Electric currents act very similar to water currents. The way that we measure an electric current is using an ammeter, and we measure in a unit called the ampere, or ampere if you're an American. You can give that the symbol A, and a lot of times we'll just shorten that to amp. So you may have heard of a 12 amp motor. That just means that the motor uses a current of 12 amperes. The symbol for current is an I. I is defined as the charge flowing by a point over time, and so an amp would be a coulomb per second. An amp is actually a very large unit for current. In order to have an electric current, we need two things. First, we need a source of electric potential, which is also referred to as voltage. Basically, what that means is that something to give charges energy. Energy would be the key word here. So a volt is a joule per coulomb. Remember that a joule is a unit of energy. So a 12-volt battery will have 12 joules of energy for every coulomb of charge. That's what voltage means. And so the thing typically that we use to obtain electric potential is a battery. The other source of electric potential would be the electrical outlets, but that's kind of a different kind of electric current than what we're discussing. So we're going to stick with batteries. If you consider one half of a battery, like the positive end of it, it's filled with positive charges. It's got an excess of positive charge. That's why it's called the positive end of the battery. And so a random charge in there has lots of energy because all the other positive charges are causing it to be repelled. So again, the way that we measure it is with a device called a voltmeter, and the unit is volt, or joule per coulomb. The second thing that we need in order to have an electric current is a conductive path. Remember that charges can only move through conductors such as metals. The two best conductors are silver and copper. Because copper is a good conductor, typically we make wires out of it. So if you just take a random wire like your cell phone charger or the cord to a lamp and take the insulation off of it, probably it's going to be made out of copper. Silver is better than copper, but because it's so expensive, we stick with copper. And so a piece of copper allows charges to move through it, whereas something like rubber, the charges cannot move through it. We call those things insulators. And so in order to understand how charges move and what they do, we're going to kind of compare charges moving through wires to water moving through pipes. We can use water to do work the same way that we can use charges to do work. And so water gets its energy from a water tower. You see these things in the middle of town, they're really tall. We put the water at the top of them to give the water gravitational potential energy. Just like we give charges electrical energy by putting them in batteries. The difference is that a battery has to have two ends, whereas the water tower, all we need is the one end. Water moves through pipes the same way that charges move through wires. We can put a water wheel in the path of the water and make the water turn the water wheel, or any number of devices. The same way we can put a light bulb in the path of the charges, and as the charges move through the light bulb, they're going to heat it up, which causes it to glow. We could put lots of other devices in there. There could be a TV and cause the TV to glow. It could be a motor, and the motor could spin, turn something like a fan, for instance. Now, as the water goes through the water wheel, it's going to lose some energy. Basically, it's going to slow it down. Just like as the charges move through the light bulb, they're going to lose energy. Finally, the charges have to be able to get to the other end of the battery, or the negative end of any battery, really, the same way that the water has to have a place to exit the pipe at the bottom. If we were to take something and put it at the end of the pipe and cap it off, that would be the same as not allowing the charges to get to the other end of the battery. Either way, the whole process stops. The term resistance refers to how well an object can conduct charge. Basically, it's a measure of how good a conductor is. The better conductor you have, the lower its resistance is going to be. The way that we define resistance is as current per unit volt. The symbol for resistance is a capital R, and the unit that it's measured in is called an ohm. Ohm is named after a guy, a Dutchman, I believe. The symbol for an ohm is the Greek letter omega. It's kind of like a horseshoe that's narrower at the bottom than it is at the top. So again, that's the Greek letter omega, which is the symbol for an ohm. So what that means is the more ohms a particular object has, the more difficult it is to make charges move through it. In a circuit, a resistor is going to do two things. First of all, it's going to reduce the current, and second, it's going to convert electrical energy to thermal energy. A light bulb is an example of a resistor. It's going to make the current smaller, and it's also going to take electrical energy and convert it to thermal energy. That's why a light bulb glows. That's why a light bulb feels hot. So the resistance of an object depends on three things. First, the material it's made out of. Copper is a good conductor, and so things made of copper have low resistance. Rubber is a poor conductor, and so things made of rubber have really high resistances. The second is the length of the object. The longer it is, the higher its resistance. And then the third thing is the width. The wider it is, the lower the resistance. Drawing this back to fluids and water moving through pipes, think about trying to drink a milkshake through a straw. The wider the straw is, the easier it is to drink the milkshake. The longer the straw is, the harder it is to drink the milkshake. Imagine trying to drink a milkshake through a garden hose. Garden hose is really, really long. It will be very difficult to drink a milkshake. Very, very similar with resistors. Longer resistors, it's harder to make charges move through them, whereas narrow resistors are also hard to make charges move through them. And so here's a picture. That area would represent the width. This would represent the length, and charges would move through the resistor that way. Compare that picture to this picture and decide which one should have a higher resistance. Because the picture on the left shows something that's longer and narrower, that picture represents something with a very high resistance, whereas this picture represents something with a very low resistance. So if we want to make wires to transmit electricity efficiently, we would probably choose something more like this to make our wires out of. Two more terms that we need to know. The first is the term superconductor. A superconductor is a material that has zero resistance. That means that charges move through them without losing any energy. We have materials that can be superconductors, but the problem is that we have to keep them very, very cold, like liquid nitrogen or liquid helium cold. So one of the goals of physics studies today is to try to come up with superconducting materials that'll be superconductors at room temperature. And then the other term we need to know is semiconductor. A semiconductor is a material that has a low resistance only under certain conditions. For example, there are some things that when you squeeze them will conduct electricity, but when you don't squeeze them, they won't conduct electricity. And so things like that are useful for making things like touch screens and buttons, where you want them to conduct only when certain things are done to them. Semiconductors are very, very useful things, and that's another important field of physics research today. So, to kind of quickly recap, we have a current whenever we have a flow of electric charge. And current is simply coulombs per second, measured with an ammeter. We have to have a source of electric potential in order to make charges move. We measure electric potential with a tool called a voltmeter, and a volt is simply a joule per coulomb. And we have to have some sort of path for them to move through. We kind of compared charges moving through wires with water moving through pipes. And so whenever you get confused about anything involving electric current, think back to that analogy. And then we kind of defined conductor a little bit more precisely using the term resistance, which is a measure of how well an object conducts. We need to know what resistors do. They reduce current, so the higher the resistance, the lower the current, and they also convert electrical energy to heat, to thermal energy. And then we need to know the three things that affect the resistance of an object, namely what it's made of, its width, and its length. And then things like superconductor and semiconductors are two specific cases of that, and we need to know those two terms. If anything that I've said today doesn't make sense, or you need more help and more clear explanation, please let me know. Of course, we'll do more practice with this in class. Thank you and goodbye.